Hello, this is Jan, and I will give you an overview about what happened in the last months, the last years with SimpleForest. SimpleForest is a ecological, meaningful tree modeling software. I will present you the software as it is. It is a plugin in the Computree platform. I will also talk about Computree capabilities. I will talk a little bit about free software, which is open source software, and then we will go more to the theory behind SimpleForest. I will define what a QSM is, and we will look into some statistic capabilities, and then we will get to the peer-reviewed results and check how well SimpleForest performs. So SimpleForest takes as input 3D point clouds of forest sceneries. Here we see a high resoluted 3D point cloud, and if we reduce the point cloud density, we can see a little bit better the structure of the single branches and stems. So this is the same point cloud, and we can perform with SimpleForest filters. So in the next step we will filter the ground points, and we can zoom onto the ground points, and then with SimpleForest we can also, everything is fully automated. We can fit a DTM. A DTM is a 2D image, and each raster cell contains height values. So at the border there is quite large cells, but here the resolution is a lot more refined. And we can see here on the ground points the digital terrain model is blended in as well. So if we remove the points, we see the quite fine resoluted digital terrain model with a forest road. Here is the same data. We see on the left the point cloud, and the forest road points are colored in red, and here we can see clearly the same structure. So above the DTM we have the segmentation. We can already remove some lower vegetation and the trees remain, and then we can also in an automated manner cluster these clouds, and each tree gets a different color. That means that we have subdivided all this vegetation here into meaningful tree subpoint clouds. So this is just another of the same plot. We have the segmented trees. Each tree has a different color. The color green is quite frequently used, but that it is still that the those green trees are subdivided from each other and not clustered as a single tree. So the segmentation is performs fine and really well. We can build so-called QSMs out of this cloud. We see it here. It's cylindrical models which are topologically ordered. So we fit thousands and 10,000 and 100,000 of cylinder into each tree subcloud. We can see those cylinders have at the twigs. We might suspect here overestimation. So we can also run ecological filters on the tree models, and then this improves the radius prediction of all these cylinders. If we zoom in, we just get another view on the trees. So let's look at some statistics which we can extract with the SimpleForest. So each cylinder has obviously a radius. The closer we are to the twigs, the smaller the radius gets. So green is small radius, and blue or purple is quite large radius. Um, so the traditional branch order. So this is the stem. We go here up. This might still be the stem. We go up to here. So if we color each branch order differently, the stem is branch order 0, dark green. We can see that we have here at the outer perimeters of the tree quite red. So a large branch order. But still, those twigs are green. So the traditional branch order doesn't correlate that well to the radius, and that's a bit annoying. So SimpleForest also defines something which is called the reverse branch order. We will see later how it is defined. And now we can see that all the thin structure has the same color. So this is a low reverse branch order, and the root gets a large reverse branch order. We can also visualize with CompuTree the growth volume. This is a parameter I present in my 2015 paper, SimpleTree. And for each cylinder, we can also look if it grows vertically, then it's blue, or more horizontally, then it's greenish. So green is horizontal branches, and blue is the vertical growing direction. Orange is the intermediate one. As we have input point cloud and something like cylinders where we can get QSM statistic parameters from, we can transfer these parameters to the point cloud. And then, for example, so here it's not a QSM anymore, it's like the input point cloud of a tree, but we can transfer QSM to the point cloud, and then we have ecological meaningful clusterization possibilities for the point cloud. So all twig points are colored green, the major branching structure is blue and purple, and orange is the intermediate one. So what can CompuTree give to us? So first, CompuTree is an open source platform, and SimpleForest is just a plugin for the embedding framework CompuTree. So both are open source, and we use a Qt library for the user interface, which we can see here. We have 4 visualizers open, all with a shared camera view. And here on the left is a step manager. Let's have a quick look what we have. So the visualizer here, the large window. I mean, we can just blend in something like a point cloud or a QSM or a DTM. Here we see again the ground points, which are just now filtered. So we can see here remaining trunks, which are not ground points, or like dead trees lying on the ground here on the right side. And those are colored in red and just about to be filtered out. And everything we can control in this visualizer window, which has these buttons on top of it. So as I said, we can have multiple visualizers open next to each other with a shared camera view. Here we see like really nicely the cylinder model next to the input point cloud. And also we can select objects like a single cylinder and get additional information. So here we see a lot of numbers popping up, which are like parameters of the cylinder. And we can read, for example, the radius and a lot of other stuff. CompuTree has also can blend in logging information. So during the computation we get like additional text output in the logger window. We can check how much a filter filters out of the point cloud in percentage numbers and in absolute numbers and stuff like this. So this is like the step manager. We can see here the progress of the computing step, which is just at the bottom. The 12% is done of the statistical outlier filter. And we can see here we can put like a lot of steps. One step takes the output of the previous step. And so we filter, we segment, we filter again the segmented clouds, and we build our tree models. Can be a huge pipeline of single steps. So if you add a single step, you get this kind of dialog where you can, if you want, adjust parameters. Here we have a simple step with a single parameter. The majority of steps doesn't require a lot of parameters, and all should run also decent with default values. But here you can also see my QSM step, and I designed it to give like really a lot of options to play around, to investigate everything in depth. And this is just like another step dialog where you could theoretically adjust parameters, but overall you just stick with the default values and are fine. So I also quickly want to talk about free software in general. So let's read. Free software means software that respects users' freedom and community. Roughly, it means that the user has the freedom to run, copy, distribute, study, change, and improve the software. Thus, free software is a matter of liberty, not price. To understand the concept, you should think of free as in free speech, not as in free beer. We sometimes call it libre software, borrowing the French or Spanish word for free as in freedom, to show we do not mean the software is gratis. So free software is like really great for science and purpose, because you can access the code. So first of all, you can compile the code and run it on your computer for everything which you want desire that the software should perform. Then you can also, as the source code is free, you can change the source code, adapt the software to your special needs. You can also take SimpleForest and redistribute it to other users. I mean, it's absolutely legal that you share both the code and the precompiled version of SimpleForest to other people. You should just always link to me as a source. And then if you modify SimpleForest for with Freedom 1, you might also redistribute like the modified versions of SimpleForest to other users. So let's now get some insight into the QSM structure in general. So we will look how we will set up first the topology information. So a cylinder is defined by a start and an endpoint that have x, y, z coordinates both, so 6 parameters for start and end, and a radius, which is the 7th parameter. On that picture we see here P1, P2, P3 and P4, those are points, and the vector is the distance vector from the point to this cylinder. So, well, it's just simple geometry. So let's look. This is a zoom up onto a tree model, a QSM, and we can see this is multiple cylinders. Here is a small gap. So we have here in bright green 5 cylinders, and here is a branch junction, and here is a branch junction. So these 5 cylinders between the two neighboring branch junctions are stored in a so-called segment. A segment is a list of multiple cylinders, and the list is ordered, and the order is the first cylinder is always the nearest to the root, and the last cylinder the furthest from the root. So the root is somewhere like here on the ground, and this cylinder is the first. So let's assume this is just some really old screenshots with SimpleTree, not SimpleForest. I took some slides from my PhD defense here. So we have here the root segment, which is the only segment which doesn't have any parent. And it has three child segments, this greenish, this pink, and the orange one. So the pink one is it has again its own children, so it's an inner node. And the two other ones, which are twigs, are leaf nodes. So the root has three children. So this is everything which you need to define the topology of a QSM. And so now let's look what additional parameters we can attach like to a segment or a cylinder. So we talked about previous that there is a traditional branch order, but like branch order 0 is a stem, and we can see we have like really large radii among the stem and really small ones, and also branch order 1, this is everything which grows out of the stem. So we have here also shoots and not only the major branches. So again, like all radii which are even possible, and here as well, it's not like really well correlating with the radius, and forest ecology loves a good correlation with the radius or diameter. So if you look here at the maxima curve, I mean, this might still be good to interpret. So each branch order halves the maximum diameter or something like this. You can read from this. But can we do better? So of course we can define the reverse branch order. So we count 1 at the tip, and the closer we go to the stem, the larger the branch order gets. And this is a lot more linear correlation already. So we can also count for a cylinder, like give me all your children and the children of the children, and then look for the tips and count the tips which have a child relation to you. So a child relation is a supported tip, let's say, and we count those, and if define this as a reverse pipe area branch order. It comes from the allometric scaling theory and the pipe model theory, the justification of doing so. And if we plot, it looks like really great, but it has a slight parabolic form. So we might just want to take the square root and get a more linear predictor, the reverse pipe radius branch order. So also I talked about the gross volume, and the gross volume of a cylinder, let's say this green cylinder here, is the cylinder's volume and the gross volume of all its child cylinders. So the gross volume of a child cylinder is its volume itself and the sum of all its children, and so on until we reach a tip. So this green cylinder has these pink cylinders with a child relation, and if we sum up all these volumes of green and pink but not count the red cylinders, we get the gross volume. This is just another cylinder here, which we query, or the query cylinder is here, and we get even more pink, and a little bit more pink. Or like with different colors from my PhD defense lights. Green is a query cylinder, yellow is what we also have to add, and yeah, just different representations. So I already gave the definition of the gross volume, the cylinder volume plus its children's gross volumina. And if we plot the gross volume onto the radius, we get such a form here. We can do, instead of the volume, take simply the length to define the gross length. It's a similar pattern. Or we get the vessel volume recursive. So we talked about the reverse pipe area branch order, and if we multiply, this is a predictor for the radius, but it's just a predictor, and it's more stable than actually modeled radius, cause at least at the twigs. So the predictor is better than the true measure for the radius, and if we multiply sorry, this is an area, the reverse, so it's a proxy for the cross-sectional area, not the radius, so it's an area measure. So it's a proxy for the area, and if we multiply this with the measured calcul length of the cylinder, we get a proxy for the volume, and then we just apply the recursive definition to get the vessel volume, and this is a really nice stable function, as we can see. So this is backed up by the West, Enquist and Brown model. Like we see here a screenshot of one paper of the VBE model, and so what they say, for example, in their paper, the VBE model shows theoretically how numerous allometric scaling exponents are the results of a repeated or self-similar branching architecture. The pattern to be repeated consists of one parent branch and two or more child branches, and is shown in figure blah. This pattern is sometimes referred to as a branching node or generator, and depending on the geometric properties constitutes space-filling fractal. One of the appeals of the VBE model is that, with relatively few starting assumptions, it predicts numerous biological allometric scaling relationships within and across diverse organisms, such as plants and animals. Yeah, so self-similarity means that, like, twigs always have the same diameter, for example. So this self-similar, and we can scale it up, a tip up to the root, and have some allometric scaling relationship, which takes like form of the power function here. So they also have another hypothesis, the forest is a tree. An interesting implication of our theory is that the distribution of sizes and resources fluxes among trees withstand scales identically to the distribution of sizes and resource fluxes of branches within a tree. So if we have one large tree and 4 small trees, we have one large branch and 4 small branches within a tree. Something in that direction. I hope you get it. I mean, in the end you need to read the whole paper. I can just like put like 2 really interesting sentences, and we will see soon that this reverse pipe area filter stuff performs really, really well. And so by applying this filter, which is in relation to all this theory, the VBE theory, I mean, we strengthen the models of those authors. So let's have a look. What do we have at peer-reviewed citations? During my PhD, I made like these three peer-reviewed publications, and I have a preprint of 2021. And unfortunately, I submitted to plus one computational biology, but the academical authors questions fit for the journal scope. I have to rework it and resubmit it, but you can already read it under this link, and it has a lot of stuff to offer. So the preprint is already in a well formatted PDF, and it just got in the first round rejected, but I will resubmit and hopefully get it through the next round. So I apply here evaluation on 3 different data sets, and here on the right, this is a new filter techniques based on this VBE model, and they outperform the old filtering to correct the radius on the left side. So it's a really strong new invention. This both this reverse pipe radius branch order filter, which I describe in the manuscript in the preprint in detail. So if we look on a single data set, I also have a comparison to TreeQSM, the software of Pasi Ramonen's method. This is the green here. Red is like the old SimpleForest, but blue is the new one with a new presented filter in that manuscript, the reverse pipe radius branch order filter. And we can see here it outperforms both the old SimpleForest and the TreeQSM by far. It's really close to the 1-1 line, and the QSMs have a really strong correlation to the ground truth volume measurements. But that doesn't mean just use SimpleTree, never use TreeQSM anymore. It's more like, so what if you use 2 softwares? So let's say this good filter, the blue one, would not exist. Both have quite a decent error here, the red and the green. But there is always like a pair of QSMs, one with SimpleForest, one with TreeQSM. They belong to each other. If the predictions are really close, such as those 2 points here, we can say this is a good model. If the deviation is quite large, from here to here, this is a lot distance in the 2 predictors, we just say it's not a stable prediction, just kick out this tree. So in the end, we will, by using 2 softwares, we will have an automated filter which just kicks out badly fitted QSMs. And yeah, it's just model with both softwares and gain an accuracy. So you have to drop like half of the trees or so, but you drop the worst model once. So if I combine all data sets, I use 3 data sets with harvested ground. Here, this is just like harvested volume predictions, destructive ones versus the QSM predictions. The tropical trees, the really large ones, they are showing an underestimation. But if we zoom for those trees, like up to 5 square meters, this is a zoom in, like it's a really good prediction again on the 1-1 line. So this submitted but for now rejected paper has all of its data uploaded on a persistent data repository. All SimpleForest scripts, where as well as a persistent software upload exist. I mean, every processing script is uploaded to generate the QSM models. All the source code is open and uploaded, and all evaluation scripts in R to generate such evaluation plots which you just saw are uploaded as well. Everything is uploaded and reproducible. So if we look in the onto the different data sets like Reweely and get some accuracy measures, RMSE, CCC, R square adjusted, we see some really high good predictions popping up. 0.97, 0.98, 0.96. So it's a really strong tool, and everything is evaluated with a single software version, like 150 trees, or I don't know how many trees it has been. I don't remember at the moment. I have to look it up myself. So there is an additional reference. It's a user guide. The user guide, this is a front page. The user guide has over 100 pages, and it's about theory and theory about QSMs, such as we seen in an earlier section of these slides. I have added detailed algorithmic descriptions, and I discuss all parameters which the user can adjust. So if you read these over 100 pages, you get all the details to modify and get the best accuracy out of it. So on top of it, I mean, there is like a homepage. You see a screenshot of my homepage, and then to contact me, so I have set up a newsletter, and this is the newsletter addressed. So please, if you are interested to use, sign up here. And so I would like to thank you for listening, and also to the users who gave me valuable feedback in the last weeks, last months. I mean, you made me some really nice to hear compliments, and you made me go on that way. And thanks a lot that you use my software, that you take your time, that you write me emails. Thank you. And here is just a little bit list of references with on the last page the template did break for the slides. So this is it. Thank you and goodbye.